We've just introduced momentum in our physics class, and I thought it would be interesting to, just as optional material, just to kind of discuss what the difference between Newtonian mechanics and Einstein mechanics are. And the big difference is really in the definition of momentum. In Newton's law, momentum was mass times velocity, and in Einstein's momentum is gamma times mass times velocity, and gamma is a quantity called the time dilation factor, and it is 1 over square root of 1 minus v over c squared. This is also, if you find, you can also make a comparison between v over c and gamma, and if v over c is the hyperbolic tangent of a hyperbolic angle, then gamma is the hyperbolic cosine of that angle, and multiplying tanh times cosh gives you sinh. With Newton's model, if you use that same, if you introduce that same identity, that v over c is equal to hyperbolic tanh of phi, then you would have, from Newton's theorem, or Newton's model, you would have mc tanh phi. So the difference between the Newtonian physics and Einstein physics is essentially the difference between the hyperbolic tanh of an angle and the hyperbolic sine of an angle. Now, what I propose to do in this video is to kind of show that once we accept that the Einstein momentum is mc sinh phi, we can derive this right here, which is the kinetic energy is mc squared times cosh of the hyperbolic angle minus 1. This is kind of interesting because I think this is essentially where the equation E equals mc squared comes from. Because if you look at this one, mc squared times hyperbolic tangent squared over 2, there is no sense that there is a rest mass or a rest energy, because we're not subtracting anything for cosh 0. In this case, this is cosh phi final minus cosh of 0. So if you have, when you work out the integral of work equals force dot del x, let's see, integral force dx, and you say force is equal to integral what is it, dp dt dx. When you work out that integral, this is what you get. When you work out the integral of dp dt, when you plug in mv into that integral, you get 1/2 mv squared. But when you plug in mc sinh phi into that integral, you get mc squared cosh phi minus 1. And the trick to this is that del p del t can be separated out into kind of a string of solvable problems. We can find del p del phi, we can find del phi del beta del t, and dx there at the end. Beta is just v over c. You can kind of see how everything kind of cancels out, the del phi and del phi, the del p and del p, and then we have that del t. So we'll be left with del p over del t over here, and then we got the dx here. So then it's just a matter of figuring out each of these terms. Del P del phi is based on the MC sinh phi up here. So it is just going to be MC cosh phi. Del phi del beta has to do with the derivative of the hyperbolic arctanh. If beta is the arctanh of phi, then del beta is 1, and del tanh phi del beta is del tanh phi del phi times del phi del beta. Then we can find the derivative of sinh phi over cosh phi, which is the same as tanh phi. And work this out with what's it called, the quotient rule of, and then the quotient rule, and then we can simplify this term, the cosh squared phi minus sinh squared phi over cosh squared phi. We can simplify that in two different ways. 1 over cosh squared phi, using the identity that cosh squared phi minus sinh squared phi is 1, or 1 minus tanh squared phi, which is just dividing both the cosh squared phi by cosh squared phi and then the sinh squared phi by sinh squared phi. So this is actually what I use. Del beta del phi equals 1 over cosh squared phi. Except here it's del phi del beta, so I'm going to use the reciprocal of that, cosh squared phi. And then we have del beta del t. But here, actually, I'm not going to do del beta del t. I'm going to do a switcheroo. Combine that del x del t, dx dt, to make beta. Actually, that's beta c. And then I'll just have del beta, d beta here at the end. Dx dt is velocity. Velocity is v over c times c. Okay, now I'm going to replace beta with tanh phi. Tanh phi. And I'm going to multiply that by cosh phi over here. So I will end up with tanh phi cosh phi is sinh phi. I'm going to go ahead and multiply that c squared. So I have mc squared sinh phi cosh squared phi and d beta. But that isn't satisfactory, so let's multiply that by del phi over del phi, so that we got d beta d phi, and d beta d phi, what we saw earlier, d phi d beta was 1 over cosh squared. I think I may be doing extra work that was not entirely necessary, but you can see that this del beta del phi cancels out with that cosh squared, and we'll end up with just mc squared sinh phi d phi down at the bottom. And then when we do the integral from 0 to phi final, we'll get mc squared cosh phi. Going from 0 to phi final, we end up with mc squared cosh phi final minus mc squared cosh 0, which is just 1. So final answer, our kinetic energy is mc squared times cosh phi minus 1. Now, you may be wondering, why is it cosh phi minus 1? It looks so much different from this one. Well, let's look at the two graphs plotted on the same chart. The orange line is 1/2 times tanh squared x, which would be the Newtonian version with respect to the hyperbolic angle, and the blue line, the blue curve, is the relativistic version of the energy. If we begin zooming in on this, we see that the two curves are pretty close to identical for when the x, or v over c, is less than about 0.2, and then only when v over c. Actually, what I just had was a plot with respect to the hyperbolic angle, but if you plot it with respect to actually v over c, it looks like this. And you can see that the energy goes up to, with the hyperbolic version, the energy goes to infinity when the speed approaches 1 here. So with the Newtonian mechanics, it allows velocities over the speed of light with finite energies. But with Einstein's version, you get up to the speed of light and it has infinite, and it goes right up to infinite energy. 10, 14, 18, 20, 21, 25. If you look at all four of those functions, Newtonian mechanics in terms of v over c, Einstein mechanics in terms of v over c, Newtonian mechanics in terms of the hyperbolic angle, and Einstein mechanics in terms of the hyperbolic angle. All of those functions end up looking almost exactly the same when you get close enough to 0, but they branch out quite a bit as you get to higher velocities or rapidities. Before I finish here, let me talk about just the physical implications. What is the difference between this and this, or MC sinh phi and MC tanh phi? And to do that, I'm going to talk a little bit about how we think of motion and how it should be fixed. The first intuition that we have about motion, the ground is stationary, and so we would say something like, I go to the store. This intuition is not entirely incorrect, but the idea of the relativistic approach is to kind of treat yourself as the stationary point. The observer is the stationary point, and so when you are going to the store, instead, you're not really going anywhere. What you're doing is you're boosting yourself to a reference frame where the ground and store are not stationary. So with intuition 1, here's my home, here's the store, here's my home, this is x, this is time, so I leave my home and I go to the store. And that's my path. But the relativistic approach is, here's me, I'm standing still, but in the reference frame that I'm standing still in, my home is moving to my left or moving behind me, and the store is moving towards me. So that is the relativistic approach. Now, the difference between Now, what am I saying? Newton's laws are relativistic. And so far, I've said nothing that is inconsistent with Newton's laws. Everything I've said is consistent with everything I said is consistent with Newton's laws of motion. I'm going to add something that is still consistent with Newton's law of motion, but this is the distinction where we can make a modification. When I boost from this reference frame where, okay, the store is stationary, the house is stationary, I'm moving to the right, right? When I boost, this line comes straight over here. This event where where I arrive at the store and the same time at home, those events don't move in time. They move in space, but they don't move in time. So this event moves over to here, and this event moves over to here. Now the problem with this is that if this were a speed of light signal, if this was a light signal, well, actually, let's do a light signal that looks like this. If we did the same thing to the light signal, this event would move over. It would move over to there. So the speed of light has changed to the right. It's gotten smaller. It's slowed down to the right. We did the same thing with the speed of light to the left. Well, that speed of light would have sped up. Okay, so this is inconsistent with the special theory of relativity. What we're going to do instead to keep the speed of light constant here and here is instead of moving these events from here to here and keeping them at the same time, what we're going to do is we're going to imagine the speed of light right here and the speed of light right here. And instead of moving the events in a straight line going that way, we're going to move them on a hyperbolic arc like that. And what happens is all of the events in the spacetime move on hyperbolic arcs. And events shift along these hyperbolic arcs, which will be labeled something like, could be labeled something like r cosh phi, comma r sinh phi, because that's how to represent hyperbolic arcs. So if you've got a particle that is traveling delta x that way and delta t this way, and delta t is r sinh phi, and delta x is r cosh phi, it has a velocity. Velocity equals c tanh phi. But it turns out that particle does not have a momentum equal to, p is not equal to mv, but rather p is equal to mv cosh phi. But v is c tanh phi, and tanh phi times cosh phi is sinh phi. So